Does that mean we have to go by your house like 5 tomorrow and just lay on the floor?
Don't worry, we will.
4? What?
Okay.
Do we got to copy that down?
No. Do not copy this down, but bring out your notebooks. Here's what I want you to do. I want you to jot down, bullet point, jot down anything you can tell me about this picture up here.
I don't know. It's going down.
Anything.
Decreasing.
Okay. I want you, and it doesn't have to be earth-shattering detail. Give me anything. Anything. What? Like if somebody plopped this up. You've seen this before, guys. You've seen this last year. But it applies to what we're talking about now. Tell me what the words mean. Tell me why the line's going down. Tell me this word half-life, this word radioactive, this word decay. You've got C14 atoms in green. You've got N14 atoms as red. What does the C stand for? What does the N stand for? Give me anything you possibly could tell me about this. There's some fractions along the side. What are those fractions representing, and what does that mean? In other words, tell me anything and everything. Even if it's really, really, really basic. Start basic. Take a few minutes to do that while I get organized here. Okay, well, we should be talking about this start up here.
Isn't C14 something like carbon or something?
It is, yep. C stands for carbon. You guys should know that. C14. What does the 14 stand for? You should know that. Okay. Whose phone just went off? Oh, is that your computer? Okay. Sorry. No, that's okay.
What is he mine? That was mine. I was like,
I
broke mine actually.
I broke mine too. So,
and his broke yesterday.
but I didn't do that one on purpose. I would throw it on the sidewalk.
His mom called him and it broke. Serious.
Serious? I didn't talk to her.
Okay. Somebody say something. What do you think?
The line's decreasing.
The line is decreasing. Yes. What does that mean?
It's decreasing
What's
by
decreasing?
half every time.
It's decreasing by half every time.
Right here.
Go ahead, Kirsten.
As the fraction of original element remaining decreases, so does the half-life. So if you're
The half-lives aren't decreasing. The half-lives are going up.
But
No, that's okay. But I can turn what you said. I think. Well, let me try it again. Say it again. Your first part of your sentence was right.
as the fraction of original element remaining decreases, so does the half-life.
Yeah. I will agree with your first part. The fraction of original sample, which is green, is decreasing. But it's decreasing as the half-lives are increasing, going up. I will kind of modify your sentence. That's fine, okay? You guys are all trying to beat you detail. Give me something. C stands for carbon. What does N stand for?
Nitrogen.
Nitrogen, okay? So what do you think is going on in this picture? You're starting with a bunch of the green atoms, which are carbon. But as you kind of go through time, half-lives, what's happening to those green atoms? They're turning into red atoms. They're turning into nitrogen. Okay? What else can we tell me? More. Something. What does radioactive decay even mean? What does that mean?
That's how long it
It's
takes
dead,
for the radioactive material to decay.
Well, that's more of a half-life. A half-life is a time. A half-life is the time it takes for half of a substance to decay. Let me do this. I want to remind you guys, bring out the Brown's cup, filled with pennies. I got bugs here, I don't know why. Okay.
So annoying.
Okay. these pennies are representing atoms of carbon-14. This is an atom of carbon-14. This is an atom. This is an atom. This is an atom. Remember what an atom is, guys. An atom consists of protons, neutrons, and electrons. In fact, actually, guys, carbon, that's a carbon atom right here. Okay. So each of these pennies is like one of those carbon atoms. It's a little different, though. This is carbon-14. That's not carbon-14. That's carbon-12. We'll get to that difference in a minute. But each of these is an atom. This is radioactive. Radioactive atoms. What that means is that these atoms, and all the protons, neutrons, and electrons that make it up, they don't like to stay glued together. They don't like to stay like that all together. In the nucleus, where the protons and neutrons are, they don't like to stay glued. So over time, protons and neutrons just kind of go bling, 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 bling. They kind of pop off. Well, protons and neutrons are bing, 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 bing off. It's not going to be carbon-14 anymore. It's going to change into something else. Nitrogen-14 in this case. Let's say this is carbon-14, hot radioactive stuff. I take this through one half-life, which in this case is about 5,000 years. So 5,000 years go by, bam, half of these pennies are going to change into something else. In the cup, that's not working. Half of those pennies, they didn't disappear. Oh, they didn't disappear. I'd be violating the law of conservation of mass if they just poof, disappeared. But half of those carbon-14 atoms just turned into nitrogen-14, something different. And they're not radioactive anymore. Those are still radioactive. And one half-life has gone by. All right, I'm going to go another 5,000 years. Half of those are now going to change into nitrogen-14. Get the idea? Half, half, half. So theoretically, you never get to zero. You're always taking a half. Okay. That is what this picture is showing, because it is showing you start with a sample of hot C14 radioactive atoms. Each atom, they have like, what, 8 dots up there, 8 green dots. You have a whole sample of carbon-14. After one half-life, half of those green dots have now become red. Take it through another half-life, half of those green dots, which were 4, now there's only 2, half of those have now become red. And so on, and so on, and so on. This is freaky. This is what radioactive material is. Carbon-14 is radioactive, and so that just means that it's not stable. Carbon-14 doesn't like to stay carbon-14. It likes to change into something more stable. When it does that, this is what this picture doesn't show you. This is why radioactivity is so dangerous. When it makes the change from green to red, it not only makes the change from green to red, but it also emits this like invisible energy. That's the stuff that's a killer. So that's the stuff. That's why you don't want to be around radioactive materials, because, yeah, it's all fine and dandy for the atoms to be changing from one atom to another. That's not the bad part. But while it's doing this, it's emitting, it's giving off, in other words, radioactive energy. And like I said, what happens? What happens? Why is radioactive energy so bad? Because our fragile cells with fragile DNA inside of them, they don't like that energy. So what happens is if that radioactive energy is hitting your fragile cells, it's going to mutate your cells. When your cells mutate, a lot of times they just decide to die and kick the bucket. If you start damaging too many cells or cells of a certain kind, not good. Okay, so that's why you want to stay away from radioactivity as much as you can. Okay, that is carbon-14. Let me show you another graph. Same thing, very similar looking. Look, you got a line going down. Okay, we're not talking about carbon-14 anymore. We're not talking about C14. Now we're talking about something called potassium-40. But potassium-40 looks a lot like carbon-14. In fact, it is. It's radioactive, but it's not carbon. It's a different substance that's radioactive as well. But what do you notice about Oh, no, I didn't tell you this. What do you notice about this right here? Yeah, potassium-40 is different from carbon because potassium, it takes a long time for this stuff to decay. Okay. This is obviously biology class. I know it kind of feels like physical science right now from last year, but the reason we talk about this is that one of the ways that scientists date certain fossils of living organisms that existed a long time ago, like old living fossils, they use carbon-14 to do that. This is cool. Here's why. You guys are living, breathing, eating beings right now. All living organisms are. We've been over that. They all are absorbing nutrients from their environment. That's what we do in order to live. I don't care if you're a plant, bacteria, us. Well, what they fail to tell you is that while you're alive, you are also taking in, naturally, C14. You mean, Mrs. Hatcher, I'm taking in radioactive stuff naturally? Yeah, but really small amounts. Okay, yes, you are. Reason is, plants are taking in C14 from the soil and dirt and rocks. That's where it's actually the original source. We are actually going to be eating plants, or we eat the cows that eat the plants. So we also have C14 in us. One day we're all going to die, okay? When we die, obviously we don't do really much of anything anymore, especially we don't take in C14 anymore. So you kind of have you have your body, and you've stopped taking in C14, and so, okay. Once that C14's inside of you, it's going to start to decay. Unless they C14, for reasons we've talked about. So, what scientists can do is take a sample of your body, like let's say a mummy, Egyptian mummy from like 3000 BC. We'll take a sample of it. They'll look at the C14 levels of that mummy and compare it to the nitrogen 14 levels in that mummy, and they will take a ratio of those two numbers, and they could come up with a date for when that mummy was alive based on that information, based solely on just taking a ratio, a comparison of these two numbers. Because they know those numbers are going to change over time, even when you're dead. It's going to decay. That's why we talk about this in biology class. We are talking about a technique, radiometric dating, which uses the fact that you have these certain radioactive elements that are going to decay slowly over time, and it is used to date certain things. Now, like I said, if you wanted to date something living, like a living organism or a fossil or an Egyptian mummy, or something that's been around within the last 75,000 years, which is really a glimpse in the eye of science, like it's 75,000 years is nothing. You use this stuff. You use carbon-14. Okay, but if you want to date something that's 5,000 years old, you don't want to use this stuff. Potassium-40 is a half-life of basically one half-life is 1.3 billion years. So it takes 1.3 billion years for a given sample of potassium-40 for half of it to degrade, to decay. That's a long time. And that's pointless to date something 5,000 years old using this stuff. But this stuff has been very useful with coming up with, wake up. This stuff's been very useful for coming up with the age of the Earth. Okay, Earth has been around for 4.6 billion years. How do we know that? We've tested the potassium-40 levels in rocks to get this number. Because potassium-40 is naturally occurring in rocks. So we can take samples of rocks and figure out when those rocks were formed. And most of the rocks have been around since a long time. So they can come up with these dates for that. They can come up with 4.6 billion years for that. Okay, one more thing I want to talk about with you guys. Another challenge I have for you guys. You guys should be able to do this. C12, C14. Write those down and give some space between the two. These are symbols used to represent carbon atoms. That's a certain carbon atom. That's a certain carbon atom. I'm going to put a star next to this one because this is the one that's radioactive. You guys, this is what I want you to do. I want you to, remember last year you had to draw all those pictures of atoms with the little energy levels, and you had to fill in little dots. And I want you to draw me an atom for each of these, showing me where the protons, neutrons, and electrons would be. Go. You should have no problem with this. I'll get you started. That circle's representing a nucleus, the inside of the atom, like where the red and white circles would be. Dotted line represents an energy level. Another dotted line represents an energy level. Fill this in with the protons, neutrons, and electrons. Do the exact same for the carbon C14. Huh?
Is it 2 on the first level? 2, 4, 8.
No. You're right about 2.
12,
2, 6.
2, 8.
2, 8. 2, 8, 8. Good. 2, 8, 8. But you won't need that many for this. Go ahead, let's see how far you guys can get. Remember, don't just do the electrons, do the protons and neutrons too. Everything. I want to see where all the protons, neutrons, and electrons would be and how many there would be. Hey, the OGT will have you do this. They've done this every year. You have to answer a question by drawing a model of an atom. So, yeah, that's what we're doing. That's kind of why we're doing it here too. We'll go over it again. Okay, here's the deal. Carbon 12, carbon 14, both of them are carbon. Since both of them are carbon, I know for a fact both of them will have the same number of what? Protons. Stop right there. Protons. How many protons is it going to have?
6.
6. Where'd you get that number from?
Because that's like the regular carbon on the table.
On the periodic table of the elements, you find carbon, and it's located at position number 6. That 6 up there tells me that it's going to have 6 protons in this one and 6 protons in this one. And you guys should remember, protons are located in the middle, in the inside of the nucleus. Okay, another thing is going to be the same for these two atoms, and it's not the neutrons. It's going to be the electrons. This is where you have to, number one, remember that the electrons are located on the outside. Then you have to remember those rules about energy levels. The inside energy level can hold up to 2 electrons. So I drew 2 dots on both of them. 1, 2. I need to find a place for 4 more electrons because it has a total of 6. 1, 2, 3, 4. 1, 2, 3, 4. But those 4 have to go on the second energy level. All right. So up to this point, I have an atom of containing both protons and electrons, but I don't have my neutrons anymore. Guess what, guys? How many neutrons are going to be up in this atom on the top? 6. Very good. 6N is what that says. Plus 6N, 6 neutrons. Down here on the bottom atom, how many neutrons am I going to have? 8. Very good. That's how they're different. These two atoms are identical in every way except for their number of neutrons. That's why this one is radioactive. This one has a couple more neutrons than normal, which makes this atom as a whole unstable. Done like stay glued together. There is a word that starts with an I that is used to talk about atoms that have kind of variations of themselves. What's that I word? Isotopes. In other words, very good. Isotopes are atoms of the same element, carbon in this case, but they vary in the number of neutrons. That is the definition of an isotope. So somehow you guys have to remember isotopes and the word neutrons go together because that's what's different between isotopes. Okay. How are we doing on those? We're going to do more of those, by the way, before OGT time comes. But you guys really should go back and if you know, draw some atoms and make sure you know how to do that. Because I guarantee it is a question on the test, on the OGT test.
If neutral, then house gun, that's what makes a C-14 radioactive if they don't even have the charge.
That has nothing to do with whether it's radioactive or not. The charge has nothing to do with that. Radioactivity has to do with the fact that just the atom itself is unstable, usually because just too many neutrons are packed in the the nucleus. Doesn't matter. The charge has nothing to do with it. Okay, that's a good question. Charge has to do with something else we'll talk about later. All right, guys, I had just a few things. This is the reason we're bringing this up. Remember yesterday? You guys remember what we did yesterday? The word of the day was relative dating. And you guys cut out some pictures of squares and you were stacking up these rock layers as they should go. And if you listened yesterday, you should know that if I'm comparing two fossils within those rock layers, this one is definitely what than this one? This one's younger. Younger on top, just like those hunting magazines. The youngest subscription, you know, is on top, and like January was at the bottom. Okay, older, younger. Got to remember that. But remember, that was called relative dating, and that's a good technique to use if you're just trying to get a general idea for how old or young a fossil is compared to another fossil. It doesn't give you the actual date. But today's word is something called absolute dating. It's appropriate because when you perform absolute dating techniques, you are going to determine an exact age. I want an actual number. Is it 5,000 years old? Is it 6,000 years old? Is it 1 billion years old? I want an exact age. The technique that's used in this case is radiometric dating or radioactive dating, or they give it a bunch of different names. And radiometric dating uses radioactive isotopes, and we went over what that is just before, saying that these are those special atoms that don't like to stay glued together. They decay. The other characteristic that these isotopes have to have, they absolutely must decay at a steady rate. What I mean by that is this. Potassium-40 has one half-life of 1.3 billion years. Within that 1.3 billion years, potassium-40 better be breaking down at the same rate throughout that entire 1.3 billion years. In other words, potassium-40 doesn't remain 100% all the way through like a billion years. Okay, and then in just the last 300 years decide to go back down. It's steady. That's why this line is gradual. It's a steady rate. Okay. Otherwise, we wouldn't be able to use them to date anything. Okay, remember the word half-life. Think a half-life is a time. So if I've ever asked you to give me the half-life of something, you know your answer is going to be something in years or minutes or hours or something like that. It's a time. It's the time it takes for half of a radioactive sample to decay. Okay, this should all be reviewed from last year. Now, different radioactive substances have different half-lives. Carbon-14 has a half-life of 5,730 years. That's how long it takes a sample of carbon-14 to decay by half. But potassium 40, by the way, potassium is represented by a K, remember? Potassium 40 has a half-life of 1.3 billion years. Such a difference. Such a total difference. In both cases, you're talking about atoms that are decaying, but the time it takes for it, just one is more quicker than the other. That's why in the world of biology, C14 is used to date living or extinct organisms. In other words, no, I don't want to say living organisms. It's used to date how do you spell former? What'd you say? Yeah, there you go. Thank you. Former living things or extinct organisms. Thank you. Couldn't spell former. In other words, carbon-14, because its half-life is relatively short in the world of science, relatively short, you can use that to date anything that's been living on Earth. Living organisms haven't been around real long, so that's why it's very useful. K40, potassium 40, is useless dating living organism, but we can definitely use that stuff to get an idea of the age of the Earth by measuring the rocks. In other words, here's my point. Different radioactive isotopes have different practical purposes. In the world of biology, it's all about C14. Okay, here's what I want you guys to remember, and this should be all review as well, so I'm kind of going quickly. Let's say I have 100 grams of C14. Remember, grams, it's a mass. I got 100 grams of C14, that's the radioactive stuff. I take that through one half-life. At the end, I'm only going to have 50 grams of C14. If I take that through another half-life, I'm going to have 25 grams of C14. If I take that through another half-life, I'm going to have 12.5 grams of C14. You get the idea. Let's convert this to fractions, the evil fractions word. At the end of one half-life, obviously, half of my sample is left. Half of my radioactive sample. After another half-life, I only have 1/4 of my original sample that's radioactive, because 25 grams versus 100 grams, that's only 1/4. 12.5, that's 1/8. I only have 1/8 of my original radioactive sample. That's where they get the fractions from in these problems. Okay, taking it one step further. I told you, you can't go from 100 grams to 50 grams. 50 grams, the other 50 grams can't just disappear. You'd be violating the law of conservation of mass. So what happens is the other stuff gets turned to a different element, N14. So at the end of one half-life, I have 50 grams of C14 and I have 50 grams of N14. 50 plus 50 equals 100. At the end of another half-life, I have 25 grams of hot stuff, and how much of my N14 will I have here? 75 grams, because 75 plus 25 better equal 100, because I don't want to violate the law of conservation of mass. Mass can't be created or destroyed. 12.5, if you can't figure out the mass, 87.5 grams will turn into N14, and only 12.5 will be hot stuff anymore, but those two numbers add up to 100. Make sure you understand this. Again, this is all review from last year, so make sure we understand half-lives, what it means, understand that isotopes have different half-lives depending on what element it is. Make sure you understand the main point. You can use radioactive isotopes for a practical reason. To date stuff, to date fossils, to date rocks, to date other things. They're used in medical research. Has anybody ever had to get a thyroid test where they injected you with radioactive iodine?
My grandma has that.
I know Erin Jewell did, so she was actually talking about it. This is an interesting application. If you have a thyroid issue, you have a thyroid gland, and this gland just controls different metabolic activities you have. Some people's it gets a little wacky. What medical doctors do, iodine-131 is another radioactive substance, okay? But its half-life is something like 2 hours or something like that, real short. This thing decays fast. What they do is they inject iodine-131 near your thyroid gland, but on the outside of it, and they'll wait for a little bit of time to go by, and they're trying to figure out if the iodine actually gets absorbed by your thyroid gland, and that would be a good thing. That means that your thyroid gland's working. So if they inject you with iodine-131 and wait for a while, and then they find out, they take a picture of you, and it glows. So they take a picture of you, and if they see any of that radioactive material inside your thyroid gland, they're going to give a thumbs up. Cool. Obviously, your thyroid gland is doing what it should. So,
What does it do? What does it do?
Oh, it controls like metabolism and growth, mostly growth. Like if you're growing the way you should. Yep, good question. All right, I'm done talking. I want to see if you guys have been paying attention. This is what I want you to do.